Hi, I'm Parisa and I created a classification learning model on MATLAB that predicts the type of movements you make using EEG data. I did this all under 10 minutes without using a single line of code. Movement is a fundamental aspect of life, but an estimated 2.5 million Americans have lost control of their upper limbs due to a broken connection between their neural signals and their muscles, which has prevented them from living up to normal standards. But neuroprosthetics presents a solution. Neuroprosthetics are a range of devices and applications designed to pave a direct pathway between the brain and external devices. For example, prosthetic limbs. So we can use the brain to have a far more precise and intimate connection to prosthetic limbs, which helps us get closer than ever to replicating the operational of a genuine limb. So EEG is a form of neuroprosthetics that enable us to read brain waves in a non-invasive manner through electrodes caps that can be placed on a scalp. So currently, it is the most affordable and risk-free portal to accessing brainwave data from those with neurological disabilities who are deprived of motor functions. So I wanted to understand how neural patterns are classified. So to do this, I created a MATLAB model that solely uses data from EEG brain signals of 4 paralyzed individuals to accurately predict the hand movement a paralyzed individual wants to perform. So to establish the environment, I will first import the dataset into MATLAB, and for the scope of this project, I'll be focusing on user B, whose database consists of over 2,000 columns of information. And I'll be focusing my attention towards 3 primary motor functions: left hand movement, right hand movement, or no movement. So step 2, filtering the data. The first column, labeled as class, holds the numbers 0, 1, and 2, which corresponds to different types of movement. To inform MATLAB's automated system that this variable needs to be predicted, I am going to change it to categorical format. So I also filtered out unnecessary data, such as the column names that could potentially screw up our training results, and then now our data is ready for use. So step 3, training and building classification models. Now that the data is filtered, I started building a classification model by using a classification learner, which is a form of supervised machine learning. And basically the algorithm learns to classify new observations, and in our situation, the tool classifies brain signals of right and left hand movements and matches this pattern to specific motor tasks. Since I changed the name label into a categorical form, MATLAB can identify the 3 categories it has to classify. So next, I can configure the validation method. And basically, the validation divides the data set into 2 parts: a training set for the model training and a validation set for model performance. And I experimented with different settings and concluded that 25% works best for my data set. And then I clicked New Session to generate a scatter plot of database, which shows the relationship between the dataset and the predictors. I then used a machine learning model called the optimizable KNN model, which is a k-nearest neighbor algorithm that basically finds the best combination of hyperparameters, so like the left hand movement, right hand movement, or no movement, and any numbers of neighbors. And remember how we split the dataset into training and validation sets? Well, the optimizable KNN model works to make the prediction on validation sets by comparing it to the true EEG label, adjusting hyperparameters. So I further adjusted the hyperparameters of the KNN model by setting the number of interactions to 55. This basically increases the amount of hyperparameters that the model will explore and finds a wide range of configurations, making the results even more accurate. And I hit Train button to evaluate the model's accuracy. Step 4, visualization results. So the visualization of the minimum classification error depicts the error rate across 55 different iterations. I was able to monitor the model's performance and identify trends, such as how there's a gradual decrease in error rate and how it is converging to a minimum. And with every iteration, the model is optimized towards achieving higher hyperparameter accuracy, becoming increasingly adaptive at predicting the neural activity corresponding to right hand movement, left hand movement, and no movement. this Canon model reaches an exceptional accuracy of 95% and took merely 1 to 2 minutes to yield such results. So to further understand the performance of the model, a confusion matrix tool was used in which each row represents the true hand movement class, each column represents the predicted hand movement class, and each cell in the grid showcases the number of times the model made the particular prediction. At points in which the numbers are larger than 700, the model is having difficulty identifying the hand movement and is confused. While the current model processes high accuracy, there are many ways for further enhancements to be made. To reinforce the model, a diverse range of datasets can be incorporated in order to enhance the performance by enabling the detection of patterns that may be undetected through a smaller sample size. I could also expand the number of predicted outcomes, so rather than just focusing on left hand and right hand movement, I could also incorporate other actions like blinking and sighing. Like any project, I faced a variety of challenges throughout the process. For example, the MATLAB version featured in the tutorial that I followed differed from the one installed on my computer. This complicated the process by a lot because certain tools were located in different locations, so it's difficult for me to find them and locate them. However, through careful navigation and patience, I was able to find the different tools and stay on track. Thank you for staying tuned, and I can't wait to share my next replicate with you.